Good afternoon, everyone. I hope you're all well. It's Dr. Bennett here, and as scheduled, today is going to be our first review class for the final exam. So I've put together this little, oh come on phone, focus, thank you. So I've put together this little revision checklist of everything that may come up in the final exam. And over the next two classes, so today's class and then Wednesday's class on the 20th, we're going to basically split the semester into two halves, and we're just going to review what we've done, look at a couple of examples of some stuff that may come up on the exam, and prepare you as best possible for the final, which is on the 29th of April. So I'll upload this document as well as the notes that I'm going to be talking about shortly to Canvas, so that you can use this as a checklist. But basically the stuff in blue is what we're going to cover today, and then on Wednesday we're going to cover this stuff in green. There's also this stuff at the top which I'm not going to cover in these sessions because I expect you to either know it already or go away and revise this stuff on your own. So reviewing how to use basic trigonometry and the trigonometric rules, like for example, in addition to the sine and cosine rules, like the identities, like cos squared theta plus sine squared theta equals 1, that kind of thing, right? That may come up. So as I said, sine and cosine rules for non-right angled triangles, and then reviewing how to do some basic integration, and so that there's, as I've said in the past, this is not a test of calculus, but you should be expected to be able to integrate some basic functions. I know a lot of this is less critical now because basically the exam is going to be open book, open notes, because I can't stop it being that. But to save yourself time in like a pressure situation, it's important that you know the stuff. And also the use of Appendix B from the textbook. So you've seen when we've been dealing with centroids and centers of mass and that kind of thing, then you need to know where to find standard results from the textbook in order to make your life a lot easier for solutions to some of those types of questions. So have a look at that stuff on your own, make sure you're happy with that, and we're now going to kick off with this stuff here, review class 1, the stuff in blue, starting with vectors. So, starting with section 1 then, which is all about vectors. What I'm trying to do with these notes, which I'll upload to Canvas as well, as I have been doing, is try to address each of those bullet points that I gave in that typed document, and either give you a definition or something to jog your memory, or a quick example of how to deal with each of these bullet points. So this is not an exhaustive list by any means, but it's kind of like a quick revision guide to check whether you know what each of these bullet points is about, and how to potentially solve a problem for each of these concepts. So let's get into it then. So oh, and by the way, I'm back on my first choice for Gatorade flavour, so things must be looking up at the moment, because I've managed to get myself some green apple, which as we've discussed in the past is by far the best one. So first of all then, bearings. This stuff seems like a long time ago now, doesn't it? But hopefully, because we've gone on to more and more advanced things, then some of this stuff should be quite straightforward now. So bearings, of course, measured clockwise from north, and you always give 3 digits for your bearings. So, for example, if you're due east, which is 90 degrees, the bearing has a leading 0, right? So 090 degrees. And if any of you are pilots in training or have done any type of flying, whether it be light aircraft or gliders or that kind of thing, and this is the kind of language that's used on the radio, right? So I've given a couple of examples there, but just make sure this is clear in your head about, you know, if I give you a question about where an aircraft flies, you know, if it's flying due west and then flies due north, you know, a certain distance, can you work out the bearing that the aircraft is on? Also make sure that you can add, subtract and multiply vectors with a scalar. That should be fairly straightforward, but just give that a quick look over as well. Let's also quickly revise how we find a position vector. So given two points here in a three-dimensional space, we can work out the position of B relative to the position A, and we call that the position vector R sub AB. This is a position of B with respect to A, or in other words, how to map position A onto position B. And to find that vector, we take B and we subtract A from it, the coordinates of B, subtract the coordinates of A to find the position vector. And this tells us how to get from point A to point B, right? And then we can find the magnitude of this by square rooting the sum of the squares. Again, we've done this throughout the course, so all this should be fairly familiar to you at this stage. To find the unit vector in the AB direction, we take the position vector RAB and divide it by its magnitude. So we do this divided by this. So that's really all of the vector manipulation. This stuff probably will be contained in a more complex question where you need to apply this vector manipulation in order to solve a different problem. So let's have a quick reminder about dot products as well. So if we have two vectors, arbitrary vectors here, u and v, the dot product is just the sum of the components multiplied together. So we do 1 times 4 plus 2 times 5 plus 3 times 6, right? But the dot product is mainly useful for finding the angle between two vectors. So this is the formula here. The dot product of u and v is equal to the magnitude of u multiplied by the magnitude of v multiplied by cosine theta, where theta is the angle between vectors u and v. So if we'd like to find the angle between those two vectors, we rearrange this. We take the dot product of u and v, divide through by the magnitude of u multiplied by the magnitude of v, take the inverse cosine, and then we've got the angle between u and v. So there's a couple of important things to remember about this, and that is, because this part here is always positive, so the product of the magnitudes, then depending on what the value of the dot product is, that tells us something about the angle between those two vectors, right? So what I've drawn here is a quick sketch of cosine theta with respect to theta. This should be fairly familiar to you. So depending on whether our dot product is positive or negative or equal to 0, tells us something about the angle between those two vectors, right? So if u dot v is greater than 0, if it's positive, then we're either in this region here or this region over here. So the angle between u and v is either less than 90 degrees or greater than 270 degrees. If u dot v is equal to 0, that means we're on the axis here, either at 90 or 270 degrees. In either case, that means that u and v are perpendicular, right? They're at right angles to each other. And then finally, if u dot v is less than 0, it tells us that we're in this region down here. So the angle between u and v is between 90 and 270 degrees. So that's dot products. Let's have a quick look at cross products. And we've typically been using the cross product to find a vector which is perpendicular to two other vectors, right? So let's say we wanted a vector w that's perpendicular to both u and v. We just take the cross product of u and v, and that gives us a vector that's perpendicular to both. We can also use it again to find the angle between two vectors, although doing the dot product is easier, so you probably want to use the other one. We also have this unit vector in here as well. That's dot and cross products. Again, they probably won't be a question on their own, but they're useful for finding solutions to slightly more complex questions. So just make sure you're familiar with the process of both of those. You'll recall that to find the cross products, you have to find a determinant, right? So a determinant of a 3 by 3 matrix. So make sure that you're able to calculate that as well. Make sure you remember to get your signs the right way around. I've seen a few mistakes recently with people forgetting negative signs when doing the cross products and that kind of thing. So the final thing that we need to discuss regarding vectors are these things called direction cosines, and they're given by these formulae here. These angles here, theta x, theta y, and theta z, define the angles of this vector u between the positive axes in a three-dimensional coordinate system, right? But obviously useful for giving us the unit vector in the u direction, right? So to explain that, I've done just a quick example here. So let's say we have a force vector with a unit vector which has these direction cosines. Cosine theta x is 0.8, cosine theta y is 0.2, and cosine theta z is positive. So this is already telling us something about the unit vector, look, right? So you recall this is how we found the unit vector before, right, where we take the vector and divide it by its magnitude. That gives us a unit vector. It also gives us a direction cosine, right? So this is already telling us something about the unit vector. And the question is to express the unit vector in component form. So what we really need to find is the unit vector in the z direction, or the direction cosine in the z direction. We know it's positive, so that's going to give us that's going to tell us something when we start to do the solution. Usually when we see something about telling us whether the solution is positive or negative, tells us that we're probably going to have to do a square root, right? Because a quadratic equation is going to have two roots, right? It's going to have one positive and one negative probably. So this is just telling us we're going to take the positive root. And if we're going to have to do something about square roots, then that should tell us something about what we're doing to find this solution. So here we go, look, this is one of the trig identities that I was saying over here that you should revise. That's under the fundamentals heading on that revision guide. So I'm just using this identity here. The sum of the squares of the cosines of those angles gives me 1. So therefore I've just rearranged it for cosine theta z, plugged in the values that I'm given, and I'm able to rearrange that to find cosine theta z, or the unit in the z direction is 0.57. So this is my unit vector here. So that's it for vectors. Now let's move on and look at forces. So one final thing on vectors. Let's have a quick review of how to find components of a vector parallel and normal to a line. We had an example of this in homework number 1, I think, if you'd like to go back over that. But for example, let's say that we have some force vector that's at a given angle to the x-axis here. The first thing we can do is find the components of this vector f parallel to the x and y axes, right? And in that case, you're just solving a standard trigonometry problem, right, for a right-angled triangle. So here we know that f is at 80 degrees to the x-axis. So I just have to solve this triangle to find the components of x and y, and that gives me the components of the vector f parallel to the x and y axes. But we're not just restrained to finding components of a vector parallel to the axes. We can decompose a vector into components parallel to anything that we choose, right? So in the second bit down here, what I'm trying to do is find components of f parallel to OA and OB. So I'm calling this the origin here. So what I'm saying is I need to go some distance parallel to OA and then some distance parallel to OB in order to get to F. So I'm trying to map along OA and OB to get to the same place, right? Or equivalently, I can go parallel to OB first and then go parallel to OA second to get to F. So that's what I've drawn down here. And because I know the angles which are created here, I can kind of chase the angles around the triangle. So I know this one down here is 10 degrees, this one inside here is 70. Using z angles, I know this bit's 10 and then this bit's 30, and then this bit would be 30 here also. And then I can find this angle because I know these two, and then because I'm now dealing with a non-right angled triangle, then I can use the sine and cosine rules to find these lengths OA and OB. And by doing that, I've found components of this vector f parallel to OA and OB. So that's it for vectors. Make sure you're comfortable with all of that stuff, and now we will move on to forces. So the first thing that we need to review with forces is a few definitions. So first of all, the line of action, which I always abbreviate to LOA, is the line collinear with the force vector. But what does collinear mean? Well, it means lying on the same straight line as the force vector. So if you take any one of these force vectors in this little diagram over here, the line of action is a line that just goes straight through the force vector, extending indefinitely in either direction, right? Coplanar, as the name suggests that they lie on the same plane, right? Planar, coplanar. It's a good way of remembering that. So if the line of action of two forces lie on the same plane, like these two down here, then these two force vectors are coplanar. Force vectors are cocurrent if the lines of action intersect at a point, like this one down here, and we'll need this for evaluating whether systems are properly or improperly supported. So if you don't remember that, we'll get onto that later today. And parallel, obviously, if the lines of action of two force vectors are parallel, then they're parallel, right? Like these two up here. So that's the definitions out of the way. The other thing that we did, which is related to the example that we just covered regarding vectors, is find a force vector parallel and normal to a line. So there was a homework question on this. I believe it was in homework 2, where there was a car or a truck being winched through some point. It might have been at the origin, I can't remember, but review that question. So in this example here, basically we have a force applied in this direction through point A, and the rope or the cable is diverted through this point O, which is not quite at the origin, it's been shifted up, and that's trying to pull or tow a box or a crate through here like this. And the question is to find components of this force, which is an 80 Newton force in this direction, parallel and normal to the rope OB. Now there's a formula for this. The force parallel is equal to the unit vector in the OB direction, dotted with the force vector itself, multiplied by the unit vector in the OB direction. So there's a few bits that you need to fill in or work out in order to put these values inside this formula. The first thing is the unit vector in the OB direction. Well, we've just reviewed how to do that. We find the position vector ROB, and then we divide it by its magnitude. So then we can plug that into there and there. And then in order to find the force vector, so remember we have a magnitude of a force, but we don't know its direction at the moment. We need to find the unit vector in the OA direction, because that's where the direction in which the force is being applied, right? So then we need the position vector ROA divided by its magnitude, and then put it into this formula. So the force vector is the magnitude multiplied by the direction. So once we know all of that, we can put it all into this formula and find the components of the force parallel to OB. And then to find the normal components, they're just, so the parallel components plus the normal components give us the full components, right? So just rearranging what I've just said, the normal component is the force vector, subtract the parallel components. So that's how to solve an example like that. As I say, there was an example I think on homework 2, dig that out, have a look at that. That's just another example, or you can work through this one and try to get the actual solution. So that's it for forces. Now let's move on to moments. So here we are, section 3, moments. So a moment is a force times the distance, perpendicular distance to where you're assessing the moment about. So in its most simple form, if we have like a seesaw with the fulcrum point, some mass m at some distance x, where do we have to put a mass of 2m in order for the seesaw to balance out? Well, because we've got twice the mass, we only need half the distance, right? So the solution to this would be to put the box of mass 2m at x over 2, right, over this side. So in its simplest form, that's what it looks like, as we just dealing with it in one plane, right? But you'll remember we did a quiz like this in class where I had like a PowerPoint slide of a grid system, a 1 by 1 meter grid system with some origin points and then some force vectors dotted around the place, and I asked you to work out the moment of each of these force vectors about the origin O. So just to review what we did there, so let's take number 1. We have the line of action along here. That's at a perpendicular distance of 2 meters, right? So that gives us a moment about the origin of 5, which is the force, the magnitude of the force, multiplied by 2, which is the perpendicular distance. So 5 newtons, 2 meters gives us 10 newton meters. This force vector here, its line of action goes through the point O. So the perpendicular distance is 0, right? Hopefully, oh, and by the way, one thing I've forgotten here, that should be negative, right? Because we have a clockwise moment about O. So number 2, the line of action of the force vector goes through the point where we're assessing the moment about. So the perpendicular distance is 0, and therefore the moment about O is 0. And then finally, number 3, we've seen an example like this before where we have to assess the vertical and horizontal components of this force vector separately in order to work out the moment about O. We can see that it's going to be a counterclockwise moment about O, so it's going to be positive, but we need to work out the components first. So the horizontal component, 2 cosine 20, is at a perpendicular distance of 1 meter, right? So it goes through here. And then the vertical component, 2 sine 20, which goes through here, is at a perpendicular distance of 2 meters. So we have these two components added together. So then after we did that, we moved on to something called couples. And a couple is nothing more than 2 forces which act on an object to exert a moment. And they have to satisfy 3 conditions. They have to be equal in magnitude, opposite in direction, and have offset lines of action in order to induce that moment, right? So there's 3 conditions that a couple needs to satisfy. So to work out the moment due to a couple, you'll recall an example similar to this from a homework problem where I asked you to work out algebraically the moment due to a couple of couples, right, acting on an object. So the sum of the moments acting on this object due to these couples, so I have an F1 couple and an F2 couple. So the F1 couple is exerting a counterclockwise moment on the rectangle, right? Can you see that? And the F2 couple is exerting a clockwise moment on the rectangle. So the sum of the moments is the moment due to the F1 couple plus the moment due to the F2 couple, and they counteract each other, but we need to work out which one dominates over the other one to work out the total moment, right? So to do that, we do the cross products, right? So we take the position at which F1 acts and cross it with the force vector F1. So let's take this one first. So the point where this force vector acts is at the coordinates x1, y4, 0, right, because we're only dealing in 2 dimensions, crossed with the force vector, so F1 acts in the negative y direction. So point where the force vector acts, force vector, and then the other side of F1, So the other force vector that gives us the couple is a positive force vector in the y direction acting at the point x2, y1, right? We do the same thing for the F2 couple. And then to work out the cross products, as we've discussed just now, we take the determinant of these matrices. So we're going to have 1, 2, 3, 4 cross products to calculate, and then we're going to tidy up the answer to find the total moment exerted on this rectangle due to those couples. So just review that you're able to solve that type of question, and then we can move on to the next section of the revision guide. Oh no, we can't. The next thing we're going to look at is some more moments, this time the moments of a force about a line. We're also going to look at moments of a force about a point. So let's deal with the moment of a force about a point first. So we have an equation for this. The moment of a force about a point in 3 dimensions is the position vector r, so the position vector from the point P where we're evaluating the moment about to any point on the line of action of a force F, cross product with the force vector itself. So in this little example down here, if we have a force vector and a point on the line of action of that force vector, we can work out the moment about another point due to that force vector, right, using this formula up here. So in this example down here, we want to work out the moment about P due to the force vector F, and we know a point on the line of action of F is given by A. So what I want to do is just find out all of the information in order to put this into this equation. So first of all, I need the position vector from P to A. So I take the position of A, subtract the position of P to get that position vector, and then I just cross product that with the force vector itself. So I work out this cross product down here. So that's how to find the moment of a force about a point. Well, what about the moment of a force about a line, like a car's axle, for example? Well, we have a slightly different formula this time, which involves the moment of a force about a point. So this equation over here can be replaced into this equation here. So we take the dot product of the unit vector in the L direction, so the direction of the line which we're evaluating the moment about, dotted with the moment of the force about a point on that line, and then this is multiplied now, because this is going to give us a scalar, multiplied by the unit vector in the L direction again here. So so in this example we have the same, we have a force vector. We'd like to work out the moment about the line AB due to this force vector. So we're going to induce a moment about AB, or a torque, for example, like a car's axle. So how we do that is we take this equation, right, and we need to find the unit vector in the L direction, so that's straightforward, right? We take the position vector RAB and divide it by its magnitude. That gives us the unit vector in the L direction. And then secondly, we need MP, and as we've just seen, MP is given by the position vector from point P to any point on the line of action of the force F. So we get the the position vector RAB crossed with the force vector F. So once I've worked out this bit and this bit, then I can plug them both into this equation here and find the moment of a force about a line. So that's it for moments. Now let's move along to the final thing for today, which is all about systems, or the first half anyway, of systems in equilibrium. So finally for today then, let's have a look at the first half of systems in equilibrium, starting with what we mean by a free body diagram. So this should all be second nature to you all now. This crops up throughout the entire course. We need three things for a complete free body diagram, remember. We need vectors denoting the forces and reactions and moments. We need dimensions or angles, and we need a coordinate system so that we can apply the equilibrium equations in any given direction, right? So the next thing we looked at was what we mean by statically determinate and indeterminate systems. Well, it depends on whether we are dealing with a system in 2D or 3D. And essentially, to have a statically determinate system, we need less than or equal unknowns to the number of equilibrium equations that can be applied. So in 2D, that's 3, and in 3D, that's 6, right? Because 3 dimensions, we have the sum of the forces in the XYZ directions, and we also have the sum of the moments in the XYZ directions. So for example, so in 2D, let's say we have, we'll have a quick review of this in a second, but if we have one pin support and one fixed support, let's say, in a 2D system, we're going to have 5 unknowns and we can only apply 3 equilibrium equations, so we would have a statically indeterminate system. But let's say we have one fixed support in a 3D problem, we have 6 unknowns, and we have 6 equilibrium equations, and therefore we have a statically determinate system. So we also need to revise the types of supports in both 2D and 3D, and how many reactions and moments and in what direction they are exerted as well. So in 2 dimensions, there's only 3 possibilities: a roller, which has 1 reaction in the normal direction, a pin support, which has 2 reactions, 1 in the normal and 1 in the parallel, and a fixed support, which has 2 reaction forces and a moment which counteracts any moment. It doesn't allow twisting, right? Whereas both of these do. So we have 1 unknown here, 2 unknowns here, 3 unknowns here. In 3D, we have what's called a ball and socket, which is basically the 3D version of a pin support. So that stops the joint or the support from translating. So we have reactions in the X, Y, and Z directions, but it allows free rotation of the arm, so it doesn't have any moments, and therefore we have 3 unknowns. A roller support is exactly the same, just has 1 normal reaction force, so therefore it just gives us the 1 unknown. A hinge allows rotation only in the hinge axis, but prevents translation and rotation in the other 2 axes. So we have 5 unknowns for a hinge, and a fixed support in 3D prevents everything, right? Prevents translation and rotation in all 3 axes. So therefore we have 6 unknowns. So be sure to revise a couple of questions which use those different types of supports in both 2 and 3D. And then finally for today, we looked at what we mean by properly and improperly supported objects. And there's a technique for assessing whether a system is properly or improperly supported, and that is to draw on the lines of action of the supports and then assess where the external force is applied, right? And if the external force exerts a moment about the point where the lines of action intersect, then it's improperly supported. So you might want to dig out this handout that we did in class. These are just lifted straight from the textbook, but we did this on the overhead projector. So let's revise what we do. So if we have roller supports, we only have reactions in the normal direction, so we draw on the lines of action, right? The lines of action intersect at a single point, which I'm calling P, and then this force vector here is exerting because its line of action is offset from P, right? It's got a perpendicular distance associated with it. It's therefore exerting a counterclockwise moment about P, and therefore this system is improperly supported. Let's have a look over here. It's kind of the same, but this one has been changed to a pin support, which gives us 2 points of intersection of the lines of action, and therefore it's automatically properly supported because we have more than one intersection point of the line of action from this roller and the lines of action from this pin. So intersection point here and in here. So it doesn't matter in this case what this is doing. If we have more than one intersection point of the lines of action, it's automatically properly supported. So let's have a look at one more. Let's have a look at this one. So we have 3 roller supports. They all exert a normal reaction, and therefore they all intersect at this point P. We have a force vector down here which is offset from point P, so it's got a perpendicular distance associated with it, half L, right? So it's exerting again a counterclockwise moment about P, and therefore this system is improperly supported. So yeah, so that's it for today. That is revision class 1. We've dealt with half the semester's material just now. Basically covering most of the fundamentals that's going to be used in some of the more complex systems like trusses and frames and that kind of thing. So we'll look at some examples of that on Wednesday, and in the meantime I'll give you some more information about what the final exam itself is going to look like. So and a reminder as well about homework number 5, which is the final homework assignment. That's due this Friday at 5 o'clock. So make a start on that if you haven't already, and ask me any questions if you're stuck. So I'll speak to you all soon. Cheers.